Okay, here's my part. My name is LIU ZIHAO. I will explain the first Python script which simulates an MM1 queue using two randomseeds for arrival and service time. Okay, first we post the necessary libraries, random for generating exponential random values, and this one for plotting the simulation results. And then here we define two seeds, one for arrivals and one for services. This ensures reproducibility. The same values will be generated every time we run the code. And then here, next we generate 100 arrival times from an expansional distribution with lambda is 1.0 and 100 service time with mu is 1.2. And next, this one, here we calculate the cumulative arrival times so that we know when each customer actually arrives. And then here, now we simulate the queue. For each customer, we compare the arrival time with the current server availability. The service starts either when the customer arrives or when the previous customer is done. Then we compute the service end time. And here, now let's run the program. This graph shows the results of our MM1 queue simulation. The blue line represents the arrival time of the 100 customers. The orange line shows when each customer starts being served, and the green line shows the service end time for each customer. So we can observe that when the system is not busy, the service starts right after arrival. This is when the blue and the orange line overlap. But when there is a queue, the service start is delayed, so we can see a gap between the blue and the orange line. The green line is always after the orange line, showing the duration of service. So we also observe some steeper steps in the blue line, which means more customers are arriving close together, increasing queue length. So this virtualization confirms the queuing behavior we accept in an MM1 system with random arrival and the service times. And now, let's see another one, the second simulation, which models the waiting time for buses using an exponential distribution. So first, we export libraries for random number generation, math function, and plotting. Then we define parameters. The lambda is 0.1, meaning the average waiting time is 10 minutes. And we simulate 10,000 passengers. And here we generate 10,000 random values from the exponential distribution to simulate actual waiting times. And then here we calculate the probability density function, the PDF, and the cumulative distribution function, the CDF. Well, the PDF shows the density for different wait times. The CDF shows the probability that a wait is less than or equal to a certain value. And here, this means is 1 over lambda is 10 minutes. The variance is 1 over lambda squared is 100 minutes. And then it's the picture. So let's run the program. Okay, so this is the PDF and the histogram of bus waiting time. The blue line is the theoretical exponential PDF. The light blue bar shows the histogram from our simulation, and the red dashed line marks the mean waiting time, 10 minutes. The histogram closely matches the theoretical curve. And next one, this is the cumulative distribution function, CDF. The purple line shows the probability that a passenger waits up to a certain time. At 10 minutes. At 10 minutes, around 63 of passengers would already have taken a bus. So this simulation helps visualize how exponential distribution work in modeling real-world waiting scenarios. Okay, now let's see another one. This Pearson script demonstrates how bus waiting time follow different exponential distributions using inverse transform sampling for two different arrival rates. First one is lambda is 20 and lambda is 80 buses per minute. Okay, so yeah, the first one we define two lambda values, 20 and 80 buses per minute. Sample size is 10,000. Oh, no, sorry. 10,000. The color for histogram is PDF and CDF. The X-ray set to this one. X-ray set to 0.1 minutes to focus on short waiting times. And here we calculate two fixtures, one for comparing PDF and histogram, one for comparing CDF. So this one we use inverse transform sampling to generate exponential samples. For each sample, we draw a uniform random number U. Then apply this one. This gives us a simulated waiting time in minutes. And here is here's the picture. So let's run the program. Okay. Here we compare the probability density of bus waiting time. For lambda is 20, but 20 bus comes every 3 seconds. Longer average wait. And here this one lambda is 80, but a bus comes every 0.75 seconds, much shorter wait. So we see that lambda is 80. The histogram and PDF are steep, meaning fast services. And then it's the CDF. So we compare the cumulative probabilities. The purple line, which is the lambda is 20, shows slower rise. It takes longer to reach 90 probability. The orange line, lambda is 80, reach high probability quickly. Most people wait very short time. So this simulation clearly shows how increasing the arrival rate lambda greatly reduce both the mean and the spread of waiting times. The inverse transform method gives us full control over the distribution. Yeah, here's my part. That's all.